Swayam Prabha. Digital India. Educated India.
Okay. So now I'll talk about another way of generalizing another way of looking at mixed strategies, and also goes into this question of limited rationality or bounded rationality and so on. Okay, so when what we observe, let's go back again to the case where there are finitely many pure strategies for each player. Now, what happens is in that sort of a game is that any player, basically generically player would become indifferent between playing multiple pure strategies. You know, that's the nature in the Nash equilibrium. That's what would happen, that a player becomes indifferent between playing multiple pure strategies, and then he randomizes over those. Now, all those pure strategies are the ones that give him the best payoff. So, the best expected payoff, assuming the other guys are paying their mixed strategies. Okay, this is the structure. This is the way the Nash equilibrium behaves. Now, what that effectively means is that if any strategy is even a little bit suboptimal, if any pure strategy is even slightly suboptimal, right, it gives even a slightly lower payoff than any of the others, the player would give it 0 probability. Right? He gives it, he gives probability. He gives no even he cannot. It's irrational for him to give even a slight amount of slight weight to that strategy. Now, people have wondered if this is really representative, and can this be generalized and so on. In many different from many different angles they have thought about this. There is also an effort to try and reconcile game theory with observed data. When you observe that this is what has happened in the past, this is the way the players have played in the past, can you match that with some kind of the outcomes that game theory is suggesting? Okay. So, one of the ways people have thought about this is that this particular property, that you give 0 probability to anything suboptimal, this kind of hyper optimization is a little too strong. So, instead of players playing best responses, they say that we should just expect that players play better responses. So, they play better than something that is obviously bad, but they are very close to, they are going to be close to the best, but not necessarily the best. Okay. Which means that you have to allow for players to play occasionally, let's say, or with some small probability, a suboptimal strategy also. Okay. So, suboptimal strategies also could get some positive weight. Now, if you think about it this way, then it basically is enlarging the space of strategies in a kind of behavioral way, where you are actually bringing in behavioral characteristics, that players can make mistakes, players can get nervous, players can develop cold feet at the time of play, etc. All of these kind of human nature behavioral characteristics are somehow being attempted to bring in. So, this leads to this concept of what is called a quantal response equilibrium. Okay, so
by best response we mean one that has been reasoned in either by Nash.
No, best response really means only whatever is optimal given what others are playing. But in Nash equilibrium, the best response is it would be that a player becomes indifferent between a certain set of pure strategies, a subset of his pure strategies.
So, I think a player would have to settle on a model before he can talk of
What do you mean?
I think
he has to maximize his, no, he is just a utility maximizer.
He doesn't know what others are doing to play the
No. So, best response is assuming fixing what the others are playing. What is the optimal thing for the player to play? That is all that best response means. So, this leads to, as I said, a concept of what is called quantal response. And now the interesting thing about quantal response is because there are all these behavioral elements brought in, right. It also is very nice, very sort of easy to merge with any kind of data sciences. So, if you have lots of past data, if you want to in which say players have played in a certain way, like for example, there could be an evader and a pursuer and an evader, and this is a pursuer is trying to or an intruder that is trying to get into a network, and there are detectors trying to detect it, and this cat and mouse game between a intruder and detector has gone on for multiple rounds, and you have had data from those rounds, but you do not know what, there are some elements of the game that are not fully specified, and all you know is just this past data. Like for example, you do not know what exactly is the utility function of the intruder, you do not know what exactly is the what is exactly the utility function for the detector, etc., etc. You may not even know all the entire space of strategies that are available, and all of these things. Some of these things are just you just have this data of what has happened in the past, and from there you want to try and think about the game. So, one of the things that you can do with using the quantal response is is very easily blended in with any other kind of data scientific tool. Okay. So, I will just explain this right now. So, okay. So, to motivate this, let's look at to motivate this, we should look at this problem of what is called matching pennies. So, very simple game. Two players have two coins. Okay, the coins have two sides, heads and tails. Now, I'm writing this assuming players are maximizing. Okay, so if the deal for player 1 is that, so what they have to do is they each have two coins, they each have their own coin, and they have to decide whether they put the coin down with heads facing up or tails facing up. Okay, if both have heads, both put heads up, then player 1 gets 1 and player 2 gets 0. So, the row player gets 1, column player gets 0. If both put tails, then again player 1 gets 1 and player 2 gets 0. And on the other hand, if they do not coordinate, that means if player 1 puts heads and the other player 2 puts tails, then player 1 will get 0 and player 2 will get 1, and vice versa as well. If player 1 puts tails and player 2 puts heads, then player 2 gets 1 and player 1 gets 0. So, in other words, player 1 wins when their outcomes are the same, when the up face is the same for both players. Player 2 wins when the face is different. Okay. So, this is the setup. So, the game is you can see the payoffs and so on are extremely symmetric, and in fact you can also see that there is no pure strategy Nash equilibrium in this game. Okay. The main thing is this is a non-cooperative game, so players have to decide what they want to put without seeing what the other has put, obviously. Okay, so otherwise the game becomes trivial. So you cannot see what the other has put. So the way it's usually played by kids and all that is that they hide the face and then they reveal it and then you decide who won. Okay, so now but there is no pure strategy Nash equilibrium, but there is a mixed strategy Nash equilibrium, and in fact there is a unique one. Okay, so this has a unique. There is only exactly one mixed strategy Nash equilibrium. And what do you think that would be? Yeah, because of the symmetry of the problem, it is that each plays heads stroke tails with probability half. this is the Nash equilibrium. Now, what we will do is, we will change this a little bit. Okay, so let us change this this problem. Now, what we will replace this 1 here that I have here, this 1. This 1 is going to be replaced with capital X, okay, and X here is something positive. So, when X is 1, you get back the old matching pennies. With X not equal to 1, it is what is called the asymmetric matching penny. Okay. Now, can you tell me what is the with X positive, but any general X, there is again a unique mixed strategy Nash equilibrium. But what can you tell me what is that Nash equilibrium? Yeah. So, who plays what? What is the row player strategy? So, remember, the row player has to make the column player indifferent between his pure strategies, right? No. The row player has to make the column player indifferent between his pure strategies. The column, yeah. So, the row player actually ends up uniformly randomizing. Okay. So, the row player plays half heads and half tails. Okay. So, if he plays tails with heads with probability half and tails with probability half, the column player will becomes indifferent between playing heads or tails. Okay. And now, what about the column player? So, the column player, he selects heads with probability 1 by x plus 1 and tails with probability x by x plus 1. Now, what people have argued is that if you look at this in terms of experiments and so on, in terms of any kind of empirical data, this seems to be a little bit odd. One of the things that, for example, one of the things that happens in this is that even if you let x, say for example, go to infinity, you keep raising x to infinity, the row player continues to play half and half, although x affects his payoff. X is affecting the row player's payoff, it does not affect the column player's payoff, but his strategy remains independent of x, right. So, you get this so, the row player strategy, half heads and half tails, is independent of the value of x itself. So, you can make x extremely large, you might think. So, if you look at this payoff matrix, you might think that the row player would get more inclined towards paying x as x gets larger and larger. And behaviorally, that is exactly what people have found. When x is larger, there is a tendency to play heads more, right, for the row player. On the other hand, what is happening is that as x gets larger and larger, it is the column player strategy that is changing, and the column player starts drifting more towards playing tails. Okay. So, now one of the ways of sort of working around this is to say that, well, here the expectation is that the reason you are playing half and half here, and the reason this is 1 by x plus 1 and x by x plus 1 is because there is a strict expectation of rationality. Suppose we allow players to play suboptimal strategies with some probability, then the outcome, the nature of the outcome would change. Okay, and we will see that now. So, let us take for example. So, what people have done is they said, let us look at how people respond to alternatives. So again, as I said, at the very outset, I had told you that we are not looking for a behavioral theory to begin with, but I am just giving you a perspective of another perspective on how things have been developed. So, one of the observations that about responding to different alternatives is that you say, suppose I want a player is shown 2 different sources of light, and he is asked to pick which is the brighter source. Okay. So, if there are two sources of light, say L1 with intensities, suppose L1 and L2, then it turns out that he picks L1 with probability L1 by L1 plus L2 and L2 with probability L2 by L1 plus L2. Okay. So, this is an observation that people have made, that essentially if you give two players two different sources of light and ask them to quickly check which one is the brighter one, they pick L1 with probability, the one with intensity L1 is chosen with probability L1 by L1 plus L2, and the one with intensity L2 is chosen with probability L2 by L1 plus L2. So, if in other words, if suppose L2 is much brighter than L1, then you start tending to 1. Mostly people will pick obviously 1, the light source L2, but otherwise they would pick a light source L1 with a slightly lower probability. Anyway, the point is this is just a motivation. This was a motivation, and they said can we use this to sort of think of a different way of modeling the response of a player. So, what you can think of is that player has these choices, right? He has to put down either heads or tails, and you can think of these as sort of intensities that he is to choose from. He looks at the conditional utility that he gets from each of these alternatives. So, he looks at let's say the expected utility that he gets from each of these alternatives, expectation taken over what the others are going to play. Okay. So, averaging over what the others would play, each player looks at the pure strategy alternatives that he has, and then instead of playing the one that is the largest only, he will play them in this proportion, in the way that he was picking the light source. Okay. So, imagine that H was one light source and tails was another light source, giving you a certain utility, and you pick them with a certain probability based on the value of the utility. So, the one that gives you the higher utility, you give it just higher probability. The one that has lower utility, you give it lower probability, but you do give them some probability. Okay. So, this is how a player is becoming a better responder as opposed to being a best responder. A best responder would simply pick the best response and ignore everything that is suboptimal. But now even stuff that is suboptimal, even alternatives that are suboptimal are being played with some probability. Okay. So, this motivates a particular type of response from the player. So, let us call that, let's write that out here. So, erase this. So, suppose so I'll just set up the problem. Okay, first let's suppose you have n is your set of players, you have Si, these are your pure strategies, and you have Ui. Okay, so sigma I, let this denote a mixed strategy. So, capital sigma I is the set of mixed strategies, or in other words is a probability, which is the set of probability distributions on Si. Okay. Now, Vij, okay, this as a function, I am going to write this as a function of sigma. This is the expected utility that a player I would get when he plays a pure strategy J. Okay, so this here is the expectation summation over x minus I in S minus I of ui of so I'll carefully show you what I've written here. So here Vij, when I write Vij, here I here the I denotes the player, I is in N. Okay, J is simply the Jth is just an index for the strategy of player I. Okay, so I am looking at some particular strategy J of player I. Okay, now here sigma minus I of x minus I is simply the product of the mixed strategies of all the other players. Okay, so it's the you have some product of sigma k of xk, k not equal to I. Okay, so and this is with others playing xk. Now, if player I plays his jth pure strategy, this is then the expected payoff that he would get when others play, when the other players play mixed strategies sigma minus I. Is this clear? So, this is what he is going to get from by paying his jth pure strategy. Okay. So, you can kind of see where I am headed here. So, now we have you have expected payoffs or light intensities from every pure strategy. You can now ask, okay, with what probabilities should I be playing my various pure strategies, right? In keeping this keeping this in mind. So what you say is you assume is that player I plays pure strategy J. Okay, player I plays pure strategy J in his set of pure strategies with this probability. With this probability, Vij of Vij, okay, that was his expected utility from playing pure strategy J, divided by summation over Vij dash, where J dash runs over Si. Now, there is obviously an assumption here, V's have to be positive for this to work. So, you have to normalize, you have to add constants and all that to make sure that this works out to be an actual probability. Okay, but once the Vij's are all positive, you can see that this now is a mixed strategy for the player, because if I take the summation over J in Si of sigma ij, this sums to 1, and if the V's are positive, this is also greater than equal to 0. Okay. But remember, Vij, the way we wrote it out, this guy is a function of sigma. Vij is a function of sigma. It is a function of what the other, in particular, it's a function of sigma minus I. Actually, I should write it more clearly here. It's a function of sigma minus I. So, it's a function of what the others are playing. So, you are evaluating it for a pure strategy, a fixed pure strategy, and your expectation is taken over the pure strategies of other players. So, you are summing over x minus I here. No, with the sigma minus I probability. Sigma minus I is this. It's just simply the product of the mixed strategy. It's the probability with which the others are playing their own pure strategies. Okay. So, player K plays pure strategy xk with probability sigma k of xk. You take the product of that. So, that gives you the probability with which say x minus I is going to be played, and you are fixing your own pure strategy at xij, and you are asking what is the payoff I am going to get from that pure strategy, from my jth pure strategy. Is this clear? So, this is the xij here is the if this is a little bit confusing, I can even just put j here itself directly. So, j itself is his pure strategy. Okay. So, this here is his is the strategy in SI. Okay. So, this is what player I gets when he plays strategy J, which is in SI, and others play X minus I. Okay. Alright. So, this is, so we just suppose that this is going to be his model for response. He has his response as this model that he looks at the various utilities that he gets from his pure strategies and plays them in the proportion of the utility. Okay. Remember, this is different from the reasoning in Nash. Nash was asking that you play the best response and just that, right. Here we are saying we look at the utilities and in proportion you are going to play the various probabilities. Now, this, remember here the Vij's are a function of sigma minus I. These guys are all functions of sigma minus I. That means these are a function of what the other players are playing. Okay. So, you now will, and if, so what's happening is now you have this equation here just defines for you sigma I, that the probability the mixed strategy for player I. You can write out a similar response equation for all players. So, you will get therefore multiple coupled response equations for all the players. Okay. So, remember, so in particular, let us take the asymmetric matching pennies. For the asymmetric matching pennies, what happens is you can see V11. So, V11 is actually equal to x times sigma 21 V12. So, that means, so 1 here is heads, and so this is 1, this is 2, okay, this is 1, this is 2, and V12 would be is just sigma 22, V21 is sigma 12, and V22 is sigma 11. So, what have I written here? This is the expected utility that player 1 gets when he plays heads, assuming the others are playing, assuming player 2 is playing sigma 2. Okay. So, why do you get x times sigma 21? Because it's, you see, it's x times sigma 21 plus 0 times sigma 22. Yeah. So, so sigma ij, this is player I, jth pure strategy. Okay. So, so I am just writing H as 1 and T as 2. Heads is 1 and T is 2. Okay. So, sigma 21 is basically the probability, if you want, you can think of this as this is basically the probability that player 2 plays heads, that is sigma 21. So, sigma 21 is the probability that player 2 plays heads, and then similarly sigma 22 is the probability that player 2 plays tails. This is the probability that player 1 plays tails, and this is the probability that player 1 plays heads. Right. So, with this now we get these V's. So, these V's have to be remember a function of sigma minus I. So, so you get equations like this with sigma on the left and sigma on the right. You get equations like this for each player, right. So, how many equations would you have for player I here? There will be as many as SI, right, as many as his pure strategies, because that defines this. Okay. And then you will have one such set for every player. Okay. So, you have to solve these simultaneously to solve for the sigma. Okay. And that then is your equilibrium. That is what is called the quantal response. So, you solve these simultaneously simultaneous solution of these equations gives rise to what is called a quantal response equilibrium. Now, we can actually, for the asymmetric matching pennies, we can in fact calculate this in closed form and see what it turns out to be. Turns out that sigma 1 1 star, that means the probability that player 1 will play heads, this turns out to be equal to square root of x divided by 1 plus square root of x, and sigma 2 1 star becomes 1 by 1 plus square root of x. So, earlier remember the row player was playing half regardless of what the value of x was. That is not the case anymore. Okay. So, you get a quantal response equilibrium in which which depends on the value of x. Now, the thing with the sort of, this is all well and good trying to explain behavior, but then the problem with, once you go away from the kind of rigor and theory, the very demanding rigor and theory that we had for when we were developing the rest of game theory otherwise, the problem that you have then is that there is now too many possible variations are possible, right. There is so once you come up with some kind of a model that like this, that a player should play in proportion with the utility, then you can ask, okay, why not something else, right? Because so for instance, sigma, you can ask for something like this: sigma ij equal to Vij raised to lambda divided by summation Vij dash raised to lambda. J dash sums in, where lambda here is greater than equal to 0, is a parameter. Now, you can see this is also a model. This is a model of responding. You can solve for a quantal response equilibrium with this kind of quantal response model as well. Okay, it turns out, in fact, I can tell you what it looks like in closed form. A sigma 1 1 star now becomes x raised to lambda divided by lambda square plus 1 divided by 1 plus x raised to lambda divided by lambda square plus 1, and sigma 2 1 star 1 plus x is to lambda square by lambda square plus 1. Now, so this is obviously a generalization of what we wrote earlier. If you take lambda equal to 1, we get back the light intensity wala model. But we can have actually you can take any greater than any lambda that is non-negative, and it gives you a valid quantal response model. Okay. Now, but here also there is something interesting. We can actually interpret this lambda in a very precise way. That we can interpret this lambda as the responsiveness of the player, which means for every a small change in utility, how responsive is the player, in the sense that if you change the utility by a small amount, how much is how big a change is that bringing in the mixed strategy that he is doing. So, how sensitive is his mixed strategy to the changes in the utility, that can be tuned by changing the lambda. Okay, so so if the lambda is larger, the small changes in the utility will lead to bigger changes in his mixed strategy. So, lambda is then interpreted often as a responsiveness of the player. But you can also interpret it in another way. So, can you tell me what happens when lambda is 0? Yeah. So, when lambda is, what happens when lambda is 0 in this model? It becomes uniform, right? If so, which means if lambda is 0, he is indifferent between everything. He doesn't care basically, whatever be the utility, he is just going to blindly play a pure strategy uniformly at random. Okay. So, when lambda is 0, you have a player who basically is indifferent or doesn't care, in short, apathetic player essentially. He doesn't care about his utility. Or what happens as lambda goes to infinity? You get back the Nash equilibrium. So, if as lambda goes to infinity, so these are ratios of things that of geometric series. You can quickly check eventually the ones, if the only ones that will get positive probability. So, it's not Nash equilibrium, it actually gives you best response. So, as lambda goes to infinity, you get back best response. So, anything that is slightly suboptimal will get 0 probability as lambda goes to infinity. Okay. And in fact, it's possible to show this more generally also. You take the quantal response equilibrium and let lambda go to infinity, you get back, in a very precise way, you get back the Nash equilibrium.